Assalamualaikum and very good morning to everyone. Yang berbahagia, Profesor T.S. CHM Dr. Chan Chin Han, our distinguished speaker. Yang berusaha, Dr. Aisyah Salihah binti Kamaruzaman, the Head of Chemistry Unit, lecturers of Chemistry Unit and fellow students. Ladies and gentlemen, first of all, it is my pleasure to be the chairperson for this professorial lecture series. My name is Puan Raihana binti Muhammad Yusuf from Chemistry Unit, Center of Foundation Studies, University Teknologi Mara, Cawangan Selangor, Dengkil Campus. To bless our program today, I would like to invite Mr. Amir Murshidi bin Saifuddin from S06 to recite the doa. Please, Mr. Amir.
A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillah Rabbil Alamin. Wassalatu wassalamu ala alihi wa sahbihi ajma'in. Allahumma aftah alaina hikmataka wa anshur alaina min khazaini rahmatika ya arhamar rahimin. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul hasna idza syi'ta sahla. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azaban nar. Wa sallallahu ala sayidina Muhammad wa ala alihi wa sahbihi wasallam. Walhamdulillah rabbil alamin. Amin.
Thank you, Mr. Amir. On behalf of the Chemistry Unit, Center of Foundation Studies, we wish to extend our warm welcome and thank you to Yang Berbahagia Professor T.S. CHM Dr. Chan Chin Han, who are willing to share her expertise and knowledge to our science students. A brief introduction about our speaker. Yang Berbahagia Professor T.S. CHM Dr. Chan Chin Han is a professor at Chemistry Unit Department, Faculty of Applied Sciences, University Teknologi Mara, Shah Alam Campus. Her research interest is in physical properties of macromolecules and polymer blend, specifically to thermoplastic elastomers, solid polymer electrolytes, and fingerprinting on polymeric products. Without further ado, let's kickstart our today's session by inviting our speaker. Please welcome Yang Berbahagia Professor T.S. CHM Dr. Chan Chin Han.
Thank you very much for the kind introductions, and thank you very much for Dr. Aisha for inviting me to share some of this work that I did a little bit on the electrochemistry. Of course, later on we will follow by the lectures on the electrochemistry. Yeah. So I hope that can you see the slide now clearly?
Yes.
I hope so. Yeah. Okay, so so my name is Chan, and a lot of time people also call me just Melissa because it's easy to remember. Yeah, I'm from UITM Shah Alam, Faculty of Applied Sciences. So I attach to a few professional bodies and institute where it's actually quite important for us, especially for me, to practice chemistry, yeah, because I'm a chemist, yeah, and I believe a lot of you also you are chemists, or you are going to be chemists most likely if you will pursue your study in chemistry. Like I'm a registered chemist in the Institute Kimia, Malaysia, so that I can practice chemistry, yeah. Let's say if I have done chemical testing reports, testing analysis, and we have to issue a report, I can sign on the report. Yeah, it's like medical doctor or engineers. So chemistry, in fact, is a very special kind of science, because in Malaysia we have this registered chemist. It is equivalent status of engineer, doctor, pharmacist. So, and also I register with the MBOT, Malaysian Board of Technologies, which I'm a professional technologist, so I can also sign on the report. At the same time, I involved in like drafting standards with the Standard Malaysia in the technical committees, and the ISO standards as well. In the working committee, look into the standards related to chemistry as well as plastic, yeah, or polymer. So For my involvement in Ybhg, basically, I'm very active in the polymer division. When we look at Ybhg, we know that they are talking about nomenclature. We talk about standardizations of name for chemistry, organic compound. This is the unit that we used to talk about, to look at all this standardization. So, chemistry is not that boring. There's a lot of activities we can do besides just working in the lab or doing titrations or all this work. Not that, and we should open up all these opportunities, and you will feel exciting when you work with the people from different countries, different branches of chemistry, and working together to how to get things done. Okay, my research actually on solid polymer electrolyte. In short, that is let's say the membrane separator between the cathode and anode for battery. Also the mixings of polymer, which means we call it polymer blends. And I work a lot on characterization, which means I use instruments as well as FTIR. We use IR to check whether we have the products that conform or not, which means you have a fake product or a genuine product, in a simpler term. So, of course, as a chemist, I'm not only doing research in the lab, we're also doing a bit of publication work, like involved in editorial, like for books, as well as writing the training books for using FTIR. Also involved in like editorial board committee for different polymer journal, because mainly my field is on polymer. Those sometimes in Malaysia, this one under Taylor Francis, this one MPDI, this one under Wiley, as well as these sometimes we be the guest editors for special issues. So you see that we are busy with a lot of activities, not only working in the labs, not only teaching, but as well as publication, sharing the knowledge that we have learned in the lab with others. So today we are going to talk about electrochemistry, and I'm very happy to make use of the lecture notes compiled by these three ladies and gentlemen. They are experts in this field, and I will mainly use their slides, so of course occasionally add a few points, but basically I actually refers to their slide. Okay, so when we talk about electrochemistry, a lot of us thought that, I just study the cathode, anode, the half cell. How am I going to use about it? But you see, now we all know about renewable energy. When we talk about renewable energy, because we know that we cannot depend on the fossil fuel, we have to have a renewable energy, let's say for carbon dioxide capture, winds, solar cell, and all this, right? Have to capture those energy, and store it, and then use it. So in order to use a renewable energy, that is still a dream at the moment, it's only at a very small scale, it's not as a big scale, because we are facing a lot of limitation for energy storage, how to store it efficiently. That's battery, that is electrochemistry. That's why this field becomes very important, because we have to put in a lot of effort how to make the whole system here, the ecosystem here, to be efficient. Every tiny point here is about talking about like movement of the electron, movement of the charged entity, that to generate electricity, to store the electricity, to use the electricity. Of course, if you would like to know more, you have your handphone, you can scan the QR code, and later I can also pass these slides to Dr. Aisha, and then she can share with you. Okay, so the key point is battery. So how nice, we capture all these renewable energies into a battery there. Just keep it. When we want to use it, then reaction can take place. Electricity can be generated and sent to you. Still, of course, this is what we are working on, and a lot of scientists are working on. That's why we need a lot of manpower to do it, which means the manpower is you, the younger generations of the future scientists. So, and a lot of you that are going to pursue your higher education. Yeah, don't forget, that chemistry is a branch that you shouldn't actually just ignore it. Yeah, if you have a chance, think about it. Why not chemistry? Because we need a lot of scientists actually work on this aspect to improve the materials, the system, the device. Of course, scientists, chemists cannot work alone. We have to work with a lot of other people. So the key point is energy storage system and battery that today we are going actually talk about. And I'm sure that you have learned it. Battery is actually galvanic cell that we have talked a lot. But when we talk about galvanic cell, electrolysis, it seems that it's so far away from our daily life. In fact, no. It's just as simple as just battery. So everyone hope to have a good battery. Everyone hope to have a very efficient, cheap battery, but it works. Yeah. So that's the challenge. So our battery has to be smaller and smaller, but it works longer and longer, and we do not need to charge so much time. That is why we need enthusiasts, young people to come in, to brainstorm, to have work in the lab, to come up with a battery that for us. So why or what is the journey for mankind that look for better battery? Yeah, you see that actually 100 years ago, we already have electric car, but it didn't work well because we have the lead acid battery. But 100 years later, we have the Tesla car. Of course, it is still not really fully commercial. I mean, it's not in a big scale, but we could have it because we have battery. Now we have the good galvanic cell. As far as for handphone, in the past, we already have the wireless, but now everyone have your smartphone that we can't live without it, right? So the key is battery. The key is the galvanic cell. So the lithium-ion battery have been talking for, this is a subject of research for a long time because, of course, there are a lot of challenges, but the opportunity is actually for these electric vehicles. So what is this battery or galvanic cell? Of course, as usual, we have the cathode, we have the anode, we have the electrolyte. That's what we are going to talk about very soon in the next 2 hours or 2.5 hours. So you can see that in the market, right, lithium-ion battery still capture the most market share at the moment for rechargeable battery. So, and the first lithium-ion battery actually been introduced in 1991. Yeah. Of course, it didn't work very well in those days, but over the years, we have a lot of improvement. So different types of battery that we used before, of course, I think nickel, I'm not sure the students actually still use nickel or not, because in those days, we actually start with nickel or lead acid. We still have maybe the battery in the car. So most of us are now using the lithium-ion battery, but it's still not good enough. We need to do a lot of work to improve the battery. So what is excitement? So you see the battery research is very important. Until 2019, we have the Nobel Prize actually on lithium-ion battery. The inventors actually improve for the carbon, the cathode and the anode, as well as the electrolyte. So that now we have the smartphone, we have the tablets, we have the LCD, we have a lot of different types of electrical devices that we enjoy. Yeah. So of course, in future, it's not going to be so boring. In the case of young people, you don't feel like, okay, I don't really want to work in the lab for a long hour in the research. That's not my interest. So the work for the research in future will not be only in the lab, because it's going to be incorporated in a lot of, let's say, artificial intelligence. It's coming up in overseas 10 years ago, and it's coming to Malaysia. So in the case that you like games, you like IT and all this, but you think, okay, I still want to study chemistry, why not? So it will not be that boring. The chemistry has to incorporate it with a lot of IT elements to make the research. So don't worry, you're not going to only work in the lab. You will have chance to work with a lot of these components of the IT. And for example, this AI makes sense of things. So if you're the chemist, you might design certain sensor and then work with the IT people that incorporate the AI component so that at the same time you can actually collect a lot of data in the labs and then map with the AI for the prediction. So it is like a game, yeah? It's quite fun to have all this work done. Okay, but before we have such kind of wonderful work, yeah, in future for you, waiting for you, let's come back to the basic, our electrochemistry. So I believe, yeah, you have studied the redox reactions and the galvanic cells the weeks before. For galvanic cell is like in this, I think illustrators shows to you that is for, we have anode, we have cathode, and we have all the circuit. And then for anode, we have the oxidation that lost electron. And for the cathode, we have the reduction where we receive electron. That's all. That's it. Yeah, as simple as that. So this week, we are looking at the standard electrode potential and non-standard cell potential. Okay. So just a refresher. Yeah. Again, oxidation is loss of electron. Reduction is gain of electron. It's about electron. So electrochemistry is about losing electron, you get electron, and how the electrons move so that we can have the electricity. It's not that tough, yeah? Okay, again, yeah, a reminder, galvanic cell. So it's a simplest term is battery, huh? We have our battery like this, yeah? Because battery, galvanic cell talk about like the reaction take place by itself, which means a spontaneous reaction. Spontaneous, these terms of spontaneous means it will happen by itself. For a battery, we know that in order for a battery to work, we hope that we don't need to do anything and that battery should generate the electricity by itself. So a battery should be a spontaneous system. So for this galvanic cell, the battery, it is a spontaneous system and it is a galvanic cell because by definition, galvanic cell is a spontaneous system. So what do we have in this galvanic cell? As usual, we need to have cathode. We have at least two electrons, one cathode, one anode. And this half cell, a lot of time, they are physically separated, but not all the time. So we can, as in some cases, actually, they are actually in one cell without a clear separation. But in a lot of time, actually, we have two half cells like this, one half cell, another half cell, and then they have the external circuit and to complete the circuit. Yeah, that's how an electrochemical cell should have. Yeah. Okay, so within a half cell, what normally do we have? I would say normally is not always we have this, but normally this is what we have. We have an electrode that immersed in the electrolyte, and then whether there's an oxidation or reduction take place. If we have a zinc, for example, then if you have a zinc electrolyte, then because zinc used to be oxidized, when you see that zinc actually slowly, it seems to be like from zinc to zinc 2+. It looks like zinc slowly dissolved in the electrolyte. So that's one half cell. But in actual case, we know that half cell does not work. We need real cell, both half cell in order to complete the circuit. So this is what we will see in the lab. Now we have, let's say, this half cell. That's we have the anode, and then we have the cathode. So we have all this cable wiring to complete the circuit. We have the salt spread, and then we have a voltmeter to read the reading. This is what we will see in the labs. Yeah. But okay, if you want to represent it using a cartoon, this is the way that you represent it using the cartoon. Yeah, the anode, the cathode, and the voltmeter, and the salt spread. Okay, let's have a look because in the past, I do not know whether you have these questions. I always have these questions because in the book, we always see the anodes on the, I hope that I show to you correctly because when we look at it, it's on our left. So I hope that you see it is on my, because now I hope that because it's mirror image, and so I hope that I show to you correctly. So when you read the book, you always find that the anode is placed on the left and the cathode is on the right, right? It's always like that, yeah, because we do it on purpose, we normally write it, even present in a cartoon, we always put the anode on the left and cathode on the right, just not to confuse so many people. Yeah. So of course, as a chemist, right? Normally a chemist is not an artist. We cannot draw so nice. This cartoon here. So what is the optional that we have? The options that we have, we represent it with this cell diagram. How would I read it? Of course, I'm not sure. I'm not saying that you must read as like me. Yeah, this is my way of reading it, and I find it rather useful for me. So I normally will start to read from the left. So when I see this zinc, I will imagine, okay, this is my zinc electrode. Yeah, and this one in the zinc electrolyte, zinc electrode and zinc in the zinc electrolyte. That's what I will have. In my imagination. Okay, then. I wouldn't continue reading. No, then I come back to the right. So on my right, I have my copper electrode, yeah, in the copper electrolyte. So you see, I have zinc electrode in the zinc electrolyte. I have copper electrode in the copper electrolyte. Now, in between, I have this salt spring. So with this, I have a complete cell diagram in my mind, even though I'm looking at this. Yeah. This cell diagram, yeah, this is the one half cell, this is the other half cell. Because for chemists, we normally will write this to represent what we are seeing. So you see, but when we actually go into lab, not always the beaker that on your left must be an anode. So it is not automatically. It's just that because we want to to synchronize it with this cell diagram that we used to put the anode on the left and the cathode on the right. So that's why the picture that we show to you, the photo we show to you, this cartoon that we showed you, we always put the anode on the left. But that doesn't mean when you go into lab, whenever setup that you do, and whatever beaker that you see, the half cell that you see on your left is cathode or is anode. Yeah, the right one is a cathode. No, please check. This is only for demonstrations in the book, because in the past, we always been told on the left is anode on the left, but after a while, when I go into lab, I got confused when I was young. But eventually, then I got to know what's the problem with me by thinking that way. It's actually just for illustrations in the book. Yeah. So I hope for the students or the candidates, please take notes. When you go into the labs, not to be so confused about the left and the right of your half cell. Okay, now we come to the points that we are going to address: standard electrode potentials and the cell potential. It's like the potential energy. So the energy will flow from the system with higher potential energy to low potential energy. For example, the water will actually flow from higher to lower area because of the difference of the potential energy. That the same goes to the electron. Yeah, electron will flow from a place with a lot of electron, which means you have a lot of high potential energy. Yeah, to a place with less electron, less potential energy. That's electron potential energy, where we call it the, let's say, the cell potential. So electron will flow from the place between the high cell potential to low cell potential. So when we look at, let's say, if we imagine this the electrode, yeah, one with high potential cell potential, the other one with low cell potential, what we have is in between, the difference between the cell potential, the difference. Yeah. So what is a standard electrode potential? Is like the ideal gas, standard gas, and all this. We always fix it at a standard condition so that it's something like just a reference point. Yeah, that is very convenient for us to use. Let's say this is an example that we have the complete cell, the carbonic cell. Yeah, you see one beaker only, but this is actually rather complete. Yeah, you do not need to must have two compartments. The beaker, then only you have the left and the right, anode and cathode in two separate cells, then it's carbonic cell. Not necessary. In this case, in fact, you have a complete carbonic cell where the zinc actually emerge in the copper electrolyte, where zinc actually being oxidized and the copper being reduced. That is why after some times you see that we have like it's like the zinc actually dissolving in the copper electrolyte, but we see precipitations of copper on this copper this zinc electrode. So it's actually a complete cell with oxidation and reduction within this one cell here. So then what if we want to measure the potential difference between the cathode and the anode? That's we call cell potential. So, but cell potential, we know that this cell potential actually change with temperature, pressure, concentration. So even though we have the same cell, same cell, for example, this Daniel cell, the zinc and the copper, every time we have to, like say, inform others that, okay, my this cell actually conducted at 30 degrees Celsius, at what pressure, at what concentration, in order to have the cell potential difference. Where this value change, even though I have the same cell, if I change the temperature, if I change the pressure, if I change the concentration. So it makes communication very difficult. Yeah. Not to say it cannot be done, it can be done. But is there a way to make our communication easier? Then that's why we introduce the standard electrode potential. It is not that it must be there. No, just that, okay, it's good that we have it because it's convenient for us to use, because when everybody fix it, okay, at what temperature that we want to talk about the cell, at what pressure, at what concentration. So the variables that we have is what is the electrode, what is the cathode, what is the anode. And because we already standardized the temperature, the pressure, and the concentration, it makes our life easier. So scientists is not always I want to do a lot of works, because we also try to work smarter by introducing a lot of this kind of prefix condition, for easy communication. So, for example, for standard condition, we fix it at 25 degrees Celsius. Of course, young people, I guess, even when I was young, I always asked, why must be 25 degrees Celsius? Why must we fix it at 1 atm? Can anybody tell me why? It's actually, for a long time, nobody can give me an answer, because they just said that I was told that this is the condition I must remember: 25 degrees Celsius, 1 atm, and 1 molar. That's the condition that I must remember. But as we know, memorizing something that without a reason or a valid reason is very difficult, especially for students that with a lot of questions. So I find it very difficult. But after a long time, I realized why. There's no reason for it. In fact, there is no reason for it. It's just a set of numbers, a set of settings that we choose. Yeah, we just choose and we fix it. So in the case that you don't like, you can change it to 30 degrees Celsius. Yeah, and get everybody to agree with you. Then become the new standard electrode potential. Can this be done? Yes, this can be done. But of course, you need to spend a lot of energy to convince others to follow you, so that other people will follow you and become a new standard electrode potential. But okay, assuming that now we are convinced, okay, I don't want to go through this hard way. I agree, like all others. 25 degrees Celsius, 1 atm, and 1 molar. That's the concentration for the standard condition. So I set everything as a standard. Now I have the electrode, cathode and anode, and I want to measure the potential difference, the cell potential difference. So the potential difference has unit. The SI unit is volt. So, and very often we see the terms of cell potential and electromotive force. And in the past, you see these terms very often for galvanic cell, which means like battery, they use this electromotive force. But in recent years, Ybhg actually put this term as less preferred term. Yeah, so they do not actually recommend to you this term. They say it's actually very ambiguous. It's caused some confusion. But I'm convinced with their justification, because when I look at this term, I myself also couldn't really understand which one moves the electron. Why galvanic cell must have these terms? I'm also feel a bit difficult for me to comprehend. But now the recommended term is cell potential. But in fact, this is what we are using every day, right? Whether for electrolytic cell or the galvanic cell. So solve our problem. So what we need to do is, if there is any potential difference between the cathode and anode, we just call it cell potential. And what is the abbreviation? We just call it E cell potential. And the unit is volt. Yeah. So now here, these terms, right? When we read through, actually, it tells us that what we measure is just an overall cell potential, but not the half cell electrode potential. In fact, I remember in the past when pre-U, when I read this, it took me a while to understand what does that mean. Yeah, because a lot of text. But maybe I illustrate this with the picture where I used to think in those days, what does that mean? That paragraph means to me. So when we have cell, right? Let's say we have the anode as zinc, and then the other one is the hydrogen electrode. What we measure is the potential difference. We can get reading from this voltmeter. And we set up another cell, we also can get readings from another cell setup. So always I only have the difference. I have no idea what is the actual half cell potential, let's say for zinc, and let's say the hydrogen electron. I have no idea, because these two values are not known to me. I only have a difference. It's simple mathematics. At home, you all can try. Let's say if you have a difference of 3, and these are the two variables. You can put just in order to get the answer as 3. You can put 3, and this is a 4, a 1. You can also get 3, right? You can also get other numbers. So forever, we don't have a solution because we have two variables in one equation. We cannot solve it. And for a long, long time, that's bothered the scientists. How are we going to solve this problem? Whenever that we measure, we only measure the difference. But now, actually, if you refer to the standard reduction tables, it seems that all the half cell, right, get a value. Where does this value come from? And at the first place, we have this limitation. So, of course, we have to find a way to solve the problem. Yeah, just to solve the problem. It doesn't mean that there is no issue there. Okay, there's one day that is like the standard condition. We just fix the condition as it. Then, okay, we said, okay, to make our life a bit like not that miserable. Okay, we all agree, yeah, to take the hydrogen electron. We assume, yeah, the potential for this hydrogen electron is 0, the half potential, the half cell potential. We just assume. This is not true. This is completely wrong to have the standard hydrogen electron or the hydrogen electron potential as 0. This is a wrong value. But this is a compromise way to solve the problem. Hydrogen electron definitely got value. But if you see the tables is 0, yeah. So when we have a 0 value, when we look at it, actually for a long time, I was not convinced, how could only this particular electrode got 0 value, the rest have value, have a numbers there, yeah. That is why here, okay. So if we put it as 0, whatever the measured value that we have from the voltmeter, we just put that values to the other electrode. That in that way, we say that, okay, now at least we can solve the problem, right? So we know, in that case, we know the zinc half electrode, what is the value? In fact, that value is not absolute value. It's only a relative value. So in science, in future, when you see that, we always say, this is only a relative value, which means they solve the problem using this concept. Yeah? It's actually just better that we don't solve the problem, even though it is not really the best solutions. Yeah? In fact, in science, a lot of time we have this kind of approach to solve a problem. So that is why a lot of time no one can tell us why hydrogen has 0 electron, is 0 volt. Just because we simply put a value. In the case, we want to put the reference electrode, this hydrogen electrode, as standard is 1, not 0 volt. Can we? Yes, we can. Just that you convince others and everybody follow our reference electrode, then can have 1 volt instead of 0 volt. Why not? It can. Yeah? But okay, now since everybody agree to use 0, we agree. We agree to use 0 as well to cut short about further communication disasters with others if we want to come up with our own standard. That's all. Yeah, but that is not true that the only correct value for hydrogen electrode is 0 volt. That is something like misconcept that I think. But I hope after this lectures here, I can convince you this is only a convenience way to solve the problem, even though this may not be the best way. Okay, now let's come to the standard electrode potential. Yeah, that we need to, let's say, talk about the potential difference between the cathode and anode, where we need to find a standard electrode for us to make use of, that to have the 0 volt, and the candidates that we choose is, in fact, we choose, it's not that by default it must be hydrogen electrode, just what we choose, or the previous people, the other scientists have chosen, is the hydrogen electrode. We just assign it, okay, let's everybody agree. We just give it a 0 volt. This is just an arbitrary value. This is not the true value, but doesn't matter. Yeah, we just assume, okay, just leave it at 0, so that this one become our hydrogen. This hydrogen electrode become our standard, reference electrode, when we call it standard hydrogen electrode. Standard hydrogen electrode with this half cell, and the half cell potential is 0. Okay, so before I further stress you, do you have any questions, or any candidates have any questions? Because it is not that easy to be digested. Yeah. So, okay, let me switch on my power. Okay. Okay, I guess no questions. I hope that I convince you by this method. Okay, now have a look for this. This is what we say. We have a cell, a galvanic cell. As usual, we put our anode on our left and our cathode on our right. And because our zinc used to be anode, that's why we put this hydrogen electrode as a cathode. But sometimes you will see that our hydrogen electrode can be as an anode. It depends what is the the combination with another electrode. Okay, so when we make the measurement, because we assume this one hydrogen electrode as 0 volt, so whatever readings that we have from the voltmeter, we will devote it to the zinc electrode. Yeah, that is why we have this table now, standard reduction potential. Yeah. So this standard reduction potential is a table that we are going to refer that always present the half cell in a reduction form and with the reading of the cell potential. Yeah. So in particular, if for an oxidation half reaction, all we need to do is just to opposite the sign of the potential. Of course, reading a lot of text like this, I think it's quite tough for the candidates as well as for me. Just for your information, I'm not good in reading long text like this. Even until now, I always find it rather challenging for me. That's why I can never do good for my organic chemistry, for my biology, when there's a lot of memorizing work that I need to memorize the definition, all this, I will suffer a lot. That's why I completely sometimes understand the pain for the candidates when they have, okay, I've read this, after reading for 10 times also don't know what these texts are talking about. Never mind. Now let us just look at the tables that maybe we can manage better. This is the tables that we always been given, a standard reduction potential. So we're given all this written in a reduction form. What do you mean reduction form? Which means we receive electron. Now we receive electron. Yeah, you see all the equations here, the half reactions actually in a reduction form. And then we will be given the standard potential for that half cell. Sometimes negative value, sometimes positive value. It depends. How should we read this? Is this table important? Yeah. Let's see how we use it. Yeah. Without looking at all the text reading in the previous slide, even though they are completely correct. Yeah. But let us see. Just look at this table. Okay. When we have a negative value of the standard potential, that tells us that the reactions, because you see this sign here, yeah, can be the reaction can be to the right and can be to the left, right? So if you have a negative sign, just tell us that this reaction I don't like to be on the right, they just want to go back, to the left, just like that, meaning just like that, as simple as that, yeah. Even we can forget about whether it's oxidation or reduction or not. Just looking at the sign, okay, it's just to the left. It's quite very negative, not -3 as compared to here -0.04, which means that this one, yeah, it's just okay. I can go back to left, yeah, a bit but as compared to the lithium, this one definitely will go to the right. If we want to read this table, and here the hydrogen electron we just put 0 by default. We just put the 0, yeah, which means all this value above the hydrogen is just a relative values to the hydrogen electron. Yeah, so it all tells us that okay, the electron, all the half cell here, if it will going through, yeah, the reaction is to the left, which means oxidation. Okay, how about, yeah, we have the hydrogen electrode here, yeah. So and below it, yeah, you see positive value, yeah. The lower that we go, the more positive values that we have. That tells us that, oh, the reaction tends to the right. Yeah. So the more positive that we have, the more to the right that we have. Okay. So I hope that you get it. Yeah. So you see that the more positive value that we have for the E cell, yeah, then which means this reaction is to the right. Yeah. So, which means we have the reduction. Unlike before that, if you have the negative value, the reaction is tend to be to the left. Yeah. So when we have the lithium being reduced to lithium positive, yeah, if the reaction is to the left, what we need to do with this standard potential, I just change the sign. As simple as that, because we reverse, yeah, the direction. Yeah, just like that. Which means even without reading the long text, we can manage that. If we just get this logic, tak perlulah baca banyak-banyak the previous slide, hafalkan definasi, tak perlu. Just understand it like that, because I used to study in this way, then I can skip a lot of the definition. So if you want to reverse the reaction, just remember to change the sign. That's all. Yeah. Okay, I hope that's simple enough for everyone to grasp the concept. So now, yeah, you see that this is a reminder to have this table, yeah, and this table actually is used throughout the chapter because we have to solve problem. We have to decide which one be our anode, which one be the cathode by looking at the standard potential that we have. Okay, now let us look at the example. Yeah. So here, it also tells us that, okay, which one will have the become having the oxidation, which one be the reduction, which one is oxidizing agent, which one is a reducing agent. So is by reading here, it's good. The description is very good, but let's say for those candidates that don't like to read a lot, just go through the tables. Yeah, we just see how can we, without reading the text, can we actually have the same understanding or not? Yeah, we know that the more negative values that we have, tendency for the reaction to go from right, which means from the right to left, yeah, a lot, which means oxidation, which means going up, all these half cells tend to be oxidized more and more, tend to lose electron more and more. When it's become easier to be oxidized more and more, which means we have stronger reducing agent. That's all. As simple as that. Yeah, we do not need to look at any definition because we know that from here is easier, right, to be oxidized. So this is a very strong reducing agent. That's all. Simple, huh? Okay, now we look at the opposite side. We are going down. We have more and more positive value. That means these half cells tend to be from left to the right. From left to the right means reduction because receive electron. When it's a good having a very strong reduction going down, right? More and more reduction, which means this is a strong oxidizing agent. Stronger and stronger oxidizing agent. Yeah. So now you see that by just looking at the table, if we just look at the positive value and negative value of the standard potential, we don't need to actually refer to a lot of definition. Now we can answer. Just think for a while, which one is an oxidizing agent, which one is a good reducing agent, without memorizing the definition. Yeah. Okay. So, example. Yeah. Here, you have the zinc and the copper, and this combination is the Daniel cell. If you want to know the name of the cell, there's a name, especially with Daniel cell. If you heard about other people, okay, well, what is a Daniel cell? This is a zinc and a copper. So this is the values that you see. We always write it in a reduction form at the start as a first step. Yeah, in a reduction form, the zinc and the copper. Now you see, from the table, this is minus 0.76. This is copper. Yeah, plus 0.34. What does that tell us, right? This one seems to be reactions to the right because positive value. This one negative, it doesn't write to the right, It like to from right to the left, yeah, become, yeah, and it likes to be oxidized, yeah. So you should actually reverse this equation, yeah, by right. So in that case, which one is the reduction form? This one. So if it's a reduction form, which means this is a stronger oxidizing agent. Yeah. So which means by doing so, we don't really need to memorize, yeah, those definitions. Yeah. Because especially memorizing definition, in the past, a good memory is a plus point for a candidate, yeah? Because we have all this assessment closed book in the exam, right? You cannot bring the books inside the exam hall even for your test or your quiz, right? So you need to have good memories, yeah, for all this definition in order for us to answer the questions. But now with the computers and all these big data and all this, memory is not an asset anymore because we cannot compete with machine with good memory. And now we are in the era that, let's say, open book assessment. Now, once you Google all the information in front of you, good memories, it's not an added advantages anymore. Because if you want the definition, you just Google, you can get it. So many versions in front of you. Can you comprehend it in a short time? So it might be good that now, since you are still young, you can adapt to a new learning way. It's like, why don't we throw away a bit of try to memorize the definition, because in future, no one care about whether you memorize the definition, because you can Google, we can get it easily, yeah? And now it's just how to make use of the definition that we comprehend, then just solve the problem as this, yeah? Okay, now, so can we, since for some times that we talk about, yeah? Okay, now, can you try? I guess the candidates have questions, right? This checkpoint 4, you have the questions, yeah? Can we try? Okay, so can I check? Can I actually check? Does the candidates have these questions, because you are going to refer to? Otherwise, I can actually start like. Oh, I can't press. Why? Oh, I can't actually. It's very strange. Huh? Okay, so okay, I don't use the timer as I said, because I don't know why I cannot control. So why not, like we have let's say I show the screen, the candidates will try, and I manually use a timer. So let's say 5 minutes. Yeah, I believe you have the standard reductions table with you. Try to solve it. Do not need to worry that you forget about the definition. Just use the method that I share with you just now, and let's try. Yeah. Okay, so let's see. I guess you could have some idea. Yeah. Okay. Yeah. For A, the increasing, reducing strength, as well as for B, is that the orders that you have? Yeah. And for the increasing oxidizing strength for A and the combinations for B.
Same.
Okay, if students have any question, you may ask.
Sorry?
If students have any question.
Yeah, they can. Do they want to ask?
Prof. Chan.
Yeah. Okay, so I assume that ada questions ke? Saya tak nampak raise hand. Okay, assuming that belum ada masalah. Assuming yeah, belum lagi. So let's see, because after the stress, right, we will take a break of 10 minutes. Yeah, you have the questions, right? The solutions. Of course, you can think for a while, but it's also good that you relax your mind for some times, yeah, before we come back. Let's see. Yeah, I hope I can do the setting of the. Yeah. I cannot click. Okay, so I guess I will do it manually. Yeah, we will have the coffee break for 10 minutes. Okay, with that, I will come back. Yeah.
All right. Thank you, Professor Chan. So we're going to have a 10 minutes break and we'll see you later in 10 minutes. All right. Okay, looks like the 10 minutes break has ended. So let's continue our session with more interesting things to learn. So Professor TS CHM, Dr. Chan Chin Han, you are welcome.
Okay, thank you very much, everyone. Welcome back after the break. I hope that we are not too stressed now. We can handle for some calculation very soon. Okay, just now we talk about the cell potential for a half cell. Yeah, so that's only half cell. We need to look at the cell potential for both cathode and anode. So right now we are coming into the standard cell potential. Yeah, this one is a complete cell that with the anode and the cathode. And a lot of times as well in the textbooks, we were told this is a formulas that we need to remember to calculate the standard cell potential. Yeah, that is the standard cell potential equivalent to the cell potential, the standard cell potential for the cathode minus the cell potential for the anode. Yeah. Of course, the cell potential actually depends on the compositions of the electrode, the concentrations of the ions, and the temperature of the pressure. But I think for this abbreviation, because of this the dependence, is in fact the cell potential should be not too precise if we put it standard cell potential, because standard cell potential is just the potential difference between the anode and the cathode, where under standard condition, which means we set the pressure, we set the temperature, we set the concentration as in a standard way. That's why we have the standard cell potential. But when we talk about the cell potential, if it's not standard, if we do not have the little note here, then this cell potential, if it's not standard condition, it will change with compositions of the electrons, concentration of the ion, or temperature, or the pressures of the electrolyte. Okay, so if we have a positive standard cell potential, or as well as if you have a positive value of the cell potential, indicates that we have a spontaneous reaction, which means a galvanic cell or our battery. So for standard condition, normally the pressure that we have is 1 atm, temperature 25 degrees Celsius, concentration is 1 molar. Normally we abbreviate the zero here as the standard condition. Without the zero here is not the standard condition. Sometimes we differentiate. We do differentiate in such a way. Of course, it is not necessary. It must be as what I say, because different books or different lecturers or teachers, they might have a slightly different way to define the abbreviations that they use. Okay. So remember, this is the equations that we were told that we need to use the cell potential for the cathode minus the cell potential for the anode. Then we have the standard cell potential. Okay, that's in the standard condition. That's why we now, because it's standard condition, we can make use of the standard reduction table. Okay, have a look. So now we are asked to calculate the standard cell potential for this wild-type cell, which wild-type cell is another name is galvanic cell or battery. Under standard condition, we were told that we have 2 electrodes. Of course, if it's given this hint, we are happy. Then because from this cell diagram, we know that this is the anode, this is the cathode. For anode, we have the oxidation. For cathode, we have the reduction. If this is the anode, this is the anode, means that it has oxidation. So in the case that we were not given this cell diagram, let's say we were not given, we just were given the information here, then we have to decide which one should be our anode, which one should be our cathode. Right? So now we just look at these two values. both also look like as negative value. Yeah, both. Okay, so which one should be our anode in that case? Yeah,
The one with more negative value.
Can you speak louder, Zaki?
The one with more negative value.
yeah, the one with our more negative value should be our anode, because it doesn't like to be, yeah, from left to right, right? It has to be from right to the left, reverse, right? So this one should be our anode. This one would be our cathode. In the case if we were not being told, for this cell diagram also doesn't matter, right? Because by knowing that, looking at this value, we can guess which one should be our anode, which one should be our cathode. So now we know that this is our anode, this is our cathode. Yeah, that's why by using these formulas, yeah, then we just put in the value that this one is the anode, yeah, this is the cathode, put here, minus the value of the anode. Then we can calculate the standard cell potential, 1.25. Yeah, this is always we were told to remember to use this equation. But to be frank, until today, I have problem to remember this equation, even though it's simple enough, because I always got confused. Which one minus which one? Cathode minus anode or anode minus cathode? Cathode plus anode. I think for over the years, I never actually put in any effort to memorize this equation, even though it's very useful. So I always have a problem that what if I do not want to use this equation? Because I don't want to memorize this equation. Because why should I memorize this equation? I always have these questions. Okay, so yeah, we were given this information at the half cell and the standard cell potential. And this one, the half reactions I copy from the standard reduction table. Method one is what we discussed just now, right? Just to make use of the equation. That's why we have to remember the cathode minus the anode. Yeah. So we need to know which one is cathode, which one is anode, in a sense, because of the equation. So I always like having the other way, like okay, if even though I do not know which one is anode, which one is cathode, because I don't want to memorize it, but I know looking at this value minus 1.66, I need to flip this half reaction. I have to flip it, reverse it, right? Reverse. So when I reverse it, I must remember to change the sign. That's all. Yeah. And this one, I do not need to reverse it because I just need to reverse one half reaction, right? So that it becomes one is a receive electron, the other one is a throw electron to complete the story. Yeah. So then I try to, because it's one, now this one is oxidation, this one is reduction. Yeah. Then I can actually write like this, the overall reaction. But of course here, I haven't actually balanced the overall reaction. But as we know, balancing changed so that to balance the overall reaction would not change the value of the cell potential. It's not that when you times 2 times 3 there, that the value of the cell potential will change. It will not change. This is not the case. So in that case, right, what I need to do, right, you see, because I already reversed my half reaction, all I need to do just to add up these two. Yeah, just to add up these two to get the overall reaction. And this one, because I already changed the sign, I just add up the two. I don't even need to know which one is cathode, which one is anode. Yeah, I just make sure that I have the directions are correct, because I know that if it's minus 1.66, it doesn't like it. Just to reverse the reaction, I just add up. I can also get 1.25. Yeah, it's fine. And all the while, I've been using, I'm using this way, then I do not confuse. But because I want to share with you this way, which means if you feel that you do not want to use this equation, it's actually nothing wrong. This equation is just an equation that proposed to you. If you don't like, you do not need to use. But one thing is that you shouldn't actually change the sign and then remember this equation and use the equation, which means like you change the sign, then become like negative 0.41 minus, because you change the sign, it become positive. Then you make the whole calculation wrong. Don't mix up these two. Yeah, you can choose either one, or you can have your own way. Actually, there is no standard way to solve a solutions. I use this example to show to you that there are many ways to show to actually solve one equations, to solve one problem. There is no standard way, yeah, because this electrochemistry actually normally we teach under the branch of the physical chemistry. We know that there's a lot of formulas. We need to do a lot of calculation. It is actually difficult to remember how people do their solution, and we try to memorize their solution steps and we follow just exactly like that. No, it's difficult. And then if the candidates used to solve the problem in that manner, you will find it's very torturing to study physical chemistry or electrochemistry, because a lot of formulas that we need to remember and then we follow the steps and all this. But actually, if you understand the steps, it's like simple mathematics for primary school. You just add up summations, right? Nothing so sophisticated here. There's no equation that we need to take care of. If you couldn't remember the equation, no worry. You can still solve the problem. Yeah? Okay. So this one, I may not will go through with you, because you can use the same concept. Yeah, you can try at home because you have the lecture notes with you, and you have the answer that given the hint and the answer. Okay, now let us look at how we make use of the standard electropotential or the cell potential to actually predict whether we have a spontaneous reactions or not, or spontaneous system or not. Yeah. So here, again, we use an example of the Daniell cell. Yeah. So this is what we copy from the standard reduction table: zinc and copper in a reduction form. And then the electropotential for zinc is minus 0.76. Yeah, we know that it doesn't like from left to right. Yeah, it wants to be from right to left in that case. So it will go through oxidation. That means for our anode. So when we actually, let's say, make use of the equation, if you want, if you do not want, also never mind. Yeah? You can still come to like the standard cell potential is 1.10 volt. You have a positive value. Positive values means you have a spontaneous reaction. It's like a battery. For example, if you look at your battery, AA battery or AAA battery, it always give you like a 4.3 volts or 1.5 volts. So it's a positive value. Why? Because it is a battery. You need a positive value, yeah, to push the electron to move, to do work. Yeah. So it is a battery. So for a battery, for a galvanic cell, you need a positive value to show that this is a spontaneous cell. Yeah, but in the case that we make mistake, yeah, we make mistake. We just and that day just okay. I accidentally think that this is the copper that I should change the flip the direction. Just something wrong with let's say my thinking on that particular day, or wrongly memorize the definition. But let's say we make mistake. Yeah, and we make this as an oxidation and this one as a reduction. When we calculate, we have a negative value. So if we have this situation, as then if we want to solve the problem, right, when we know that this is a battery, this is a galvanic cell, now my standard cell potential become negative value. That's already prompt to us that we make mistake before we further make calculation. Yeah, this is Galvanic cell, right? How can I have a negative value? Which means I must make mistake to assign the cathode and the anode. Oh, the half reaction, which one is my oxidation, which one is my reaction, reduction. Okay, so it is always good that we actually check the standard cell potential to ensure that we have let's say the standard cell that's positive value for a galvanic cell. Okay, now so calculate the EMF. This is an old term. Now it become a less preferred term. We can say that calculate the standard cell potential, and state whether the reactions happens spontaneously or not. Now you see, we were given an overall reaction. So it's good now that you try to first step write the half reaction. Let's say for A first. Half reaction for nickel and zinc, and then look at the standard electropotential, and then decide which one should be your anode, which one should be your cathode, and then calculate the standard cell potential. Okay, so now we would have the break. Let's say 5 minutes for your exercise. Okay, I will do the manual timing. Please try. You will refer to your standard reduction table. Okay. So I hope that some of you already try. Perhaps you also stuck somewhere. Yeah. So could you get the answer as shown? Or you have some problem? Okay. Let's see whether I have any message that I received. Still no. So far no. Okay, I assume that so far so good. It's not easy, because I see some of the faces are from you all, but a lot of time I just have the name. I have to guess whether you have problems or not, or you're facing any difficulty. Okay, let's see. Okay, let's look at this problem. So a lot of times when we look at these equations, right, it's difficult actually for us to actually just look at it. Which one is that receive electron, which one that withdraw electron, right? So okay, and how to calculate the standard cell potential here? Yeah. So here, okay, before that. So here is the shortcut for these solutions. First, we have to basically copy from the standard reduction table, the zinc and the nickel. Yeah, zinc and the nickel. Let's see. We go back to our reduction tables. Yeah. Zinc. Yeah. Copy this. Yeah. Nickel. Copy this and write down. Yeah. So when you copy these two, that will be easier. Yeah. Or you look at this. So if you have zinc, negative 0.76, nickel, yeah, negative 0.23. So you know that zinc is more negative. If it's more negative, we know that it will tend to be oxidized. Yeah, that become our, yeah, mostly our anode. So in that sense, so however, these equations being written in such a way, right? So under normal circumstances, our zinc actually will be oxidized as zinc 2+. But now you look at this overall reaction, it's not the case. Yeah. It seems that zinc 2+ being reduced to become zinc. Yeah, then it become like the cathode and nickel to be anode. So if the calculation following this overall reaction, the cathode minus the anode, we have the negative value. So if we have this overall reaction in such a way, this is a non-spontaneous reaction. This cell is not a galvanic cell. It will not happen like this unless you provide energy for it to happen. Under normal circumstances, in fact, this reaction is not from left to the right, it has to from right to the left. If we look at the standard reduction, the reduction potential tables, right? So if it's from right to the left, we will have the cell that in a positive value, that's spontaneous reaction. Okay, so from here, you see, we can actually make prediction whether it's a spontaneous or not. We know that, like, if we want this to happen in such a way, when we calculate the standard cell potential is negative 0.53, is let's say you're a designer engineers in the factories or in the R&D lab, you can ask your boss, forget about it. It will not happen by itself. This battery will not work in that way. Yeah. So this is not a battery. So because by calculation it will not happen. No need to try. No need to try and error anymore in the lab. This is non-spontaneous. We can't change anything. Yeah. So the reaction must be in a reverse and in order for us to have a galvanic cell. Yeah. Okay. How about this? Yeah. So we know that this nickel will be oxidized as nickel 2 plus. Yeah. And then this one, the plumbum 2 plus will be reduced. So in that sense, we calculate and we have 0. It's a positive value 0.1. So which means it's a spontaneous reactions to the right. Yeah. And then here, this one, is aluminum become oxidized be aluminum 3 plus. Yeah. And this one will be our anode, and this one become our cathode. We can start to calculate, and this one 1.53 is a spontaneous reaction. So from these different way of the questions, a problem that you have, you see the problem being asked in a very different manners, right? Sometimes they give you the half cell, ask you to predict which one should be your anode, which one should be your cathode. You calculate the standard cell potential. Sometimes the overall reaction already give it to you and already fix which one is the cathode, which one is the anode. And then you start to calculate and comment whether you have a spontaneous reaction or not. So there, if we actually take this subject as by memorizing there's a lot of facts and just follow the equations that be given to us, it's actually quite tough for us to grab the concept and solve the problem. Yeah, because there's so many ways that we can actually change the problems to you and then ask you to solve that particular problem in a slightly different manner. There's no standard way to solve the equation, the problem. Okay, so before I proceed, is there any question for this checkpoint 6? Okay, I see some of your friends are shaking their heads. I believe it's okay. Okay, I'm happy to know that. Okay, after the exercise, we will take a break of the time because we already stressed ourselves for 1 hour and 40 minutes. Our brain has to be recharged a bit before we can proceed. So now we will take a break for 10 minutes before we go to the next sessions. Okay, I pass back the floor to the moderators.
All right, thank you, Professor Chan. So we're going to have a 10 minutes break. Okay, so after 10 minutes, we will continue with our lesson. All right. Encik Rizal, kita dah boleh sambung ke?
So, can we start?
Wait for signal. Encik Rizal, ada tak?
Ya.
Okey, kita dah boleh sambung ke?
Boleh. Sekejap Rafi. Cik Rafi. Okay, ready ya? Okay, ready Parai.
Okay, UiTM di hatiku. Welcome back everyone. Hope that everyone feel more refreshed after the 10 minutes break. So let's continue with our session. So Professor T.S. Dr. Chan Chin Han, the screen is yours.
Thank you very much. Welcome back after the coffee break. Yeah. Okay, let's continue. Okay, just now we talk about the standard cell potential, which means the cell potential, the whole cell, or the electrode potential, all that we discuss they are under standard condition. Yeah, 25 degrees Celsius, pressure 1 atm, and the concentration 1 molar, all standard condition. Yeah, that's a very ideal. Yeah, and not all the cell would be operating in that way in realities. So that's why now we have to deal with the non-standard cell potential here. Yeah, is there a way that we can have a quick calculation so that we know that what is actually the value of the cell potential when it is not under standard condition? That's what we are going to cover in the next few minutes. Yeah. Okay, so we know that these actually the cell potential would change when we change the pressure, when we change the temperature, as well as when we change the concentrations of the electrolyte. Yeah, so there is actually effects of the concentration of the cell potential. Yeah, even just imagine we have the two half cell, let's say the same half cell. Let's say zinc and zinc, yeah, zinc electrode in zinc electrolyte. Two identical half cell in, let's say everything is under standard condition. Yeah, 1 atm, 25 degrees Celsius, and 1 molar, both left and right, anode and cathode. So in that sense, because we have the electrode potential, both one is positive, one is negative, but same value. So what we can read from the voltmeter would be zero potential difference. There will be no potential difference between the anode and the cathode if both having the same electrode, both at the same standard condition, which means we do not have a galvanic cell. Yeah, just because our potential difference is zero. Yeah, we have a cell that in equilibrium. But what if we have two identical zinc electrode, but one the electrolyte we change the concentration, no longer standard condition, not 1 molar, maybe one is 2 molar, the other one is 0.5 molar. We change the concentration. Then we actually see the potential difference. So the reading of the voltmeter immediately is not zero. So this is the conditions that we are talking about, non-standard cell potential, and particularly in this case is the concentration effects. Yeah, when you have change of the concentration, that's why maybe now you see that the effect on concentration, if it's going to advanced level, we use a more advanced term, but actually the means the same thing. There is a concentration fluctuation, which means we fluctuate the temperature concentration, change the temperature. So for the same electrolyte, electrons will flow from the anodes. Yeah, anodes will be less concentrated solutions. Yeah, then to the cathode, more concentrated solutions. Yeah, so that's the definition that we need to know. If we have different concentration, the less concentration, then we'll put it in the anode. The more concentrated one, we'll put it as the cathode. Yeah. Okay. Let's say here, when the cell concentration, let's say we have these cathode and anodes, both are copper. When both sides having the same condition or same concentration, we will see that there's no reading in the voltmeter because there is no concentration gradient, which means there is no flow of electron. It is also wrong to say that no flow of electron, but because electron move in any case, it's just that whatever they move here and move here would be the same. That's why we don't see a gradient, kecurunan in Bahasa. We don't see the gradient, and that's why we don't see the difference in potential, even though electron actually move. But there is no, it moves in an equilibrium way, both sides. So in that case, we don't see the net flow. So when we have the 0 volt, it doesn't mean that electron sits still in both compartments. It is also not complete. It's not correct to imagine in that way. In fact, there's no net flow of the electron. But of course, if we want to make it simple, we may just say that there's no net, no flow of the electron. It is not wrong. It is not wrong, but to imagine, because of this term, that the electron sits still in a compartment may not be entirely precise also. Because a lot of the discussion we have at this pre-UNIC, we make things simple. When we make things simple, we have to take out a lot of the complicated situation in reality. So to make you the candidates to be more manageable for this subject, if we put in all the actual situations that happened in the system, then the subject become too complicated, and then you all give up, then no one want to take chemistry. Also, it's not a nice approach. So sometimes you have to give and take that, make things simple for you. But in the case that if you go to advanced level, then sometimes you were told that you have different opinion, but just be open up. Maybe at that level, you'll be given more information of a particular problem. Okay, now in the case that we change the concentrations, one is more concentrated than the other. So the less concentrated one, which means we have both the same cathode and anode with the same type of cell. Then the less concentrated one, we put it in the anode. And then the more concentrated one, we put it as a cathode. Okay. So the electrons, will be like from less to more. So you see that there will be a net flow of the current, the electron. So we can have the reading because we have the potential difference because of the concentration difference. Okay. So now we see that this one, copper become copper 2 plus. That's in the anode. Copper 2 plus become copper. That's in the cathode. Because eventually you will find that now, you see, right? Copper 2 plus is blue color. The solutions. So if it keep on having the reaction like this, eventually, copper become copper 2 plus. This cell, right, become the color, become more and more blue. This one, because copper 2 plus become copper, eventually it will be like, so blue become less blue. So after a while, eventually it will come to an equilibrium. Both have the same color of blue color, which means we have the same concentration of the electrolyte, where your reading here, the voltmeter, becomes 0. Yeah, that's how the batteries that we have, right? Initially it works, right? We have the reading. After a while, that battery dies. So 0 volt, that's why you know that it's time to change the battery. Yeah. So we need the potential difference for galvanic cell to work. But after a while, we'll come to an equilibrium, which means when equilibrium, our cell potential is equivalent to 0. That means we have to change the battery now. Yeah, it cannot do more work. Yeah. Okay. So here now, when the ion concentration are not 1 molar, yeah, for different electrolytes. Just now, what we study, both cathode, anode and cathode, same types, copper, or zinc, just a different concentration. Yeah, this okay, not that complicated, still manageable. Now both cathode, anode and cathode, that says different electrode. One is zinc, one is copper. Before that, we study all, in a standard condition. Okay, if it's standard condition, it's very simple because we fix the concentration both at 1 molar. Then we use the equation that we study, right? The standard cell potential can be calculated by potential of the cell potential for the cathode minus the cell potential of the anode. Yeah, that's very simple, straightforward. But what if now we have a different electrodes and as well as the concentration also not being fixed at 1 molar? We change the concentration. If we do so, look at the reading here. It's no longer like the standard cell potential that we calculate, right? It's no longer. It has a different value. So, will we have a more higher value or less value? It depends on the concentration that we have in the electrolytes. So this is because now we do not have a standard condition. So now means that we have too many variables, right? Now it's not in a standard condition, then we have a different electrodes, then the calculation becomes very complicated for us to manage. We need to find a way to make it simpler. Yeah, the calculation make it simpler. We also hope that, especially for beginners, they don't give up by looking at very complicated equation. So that's why sometimes like this, right? They try and error. After a while, okay, why not we make a proposal? If we do not have a standard condition, why not we develop an equation that, okay, we know the standard condition is like this. Yeah. If we develop equations that the cell potential, the actual case like this, is equivalent to the standard cell potential plus a deviation factor, which means a correction factor. What we need to do is just to calculate the correction factor, then we know what is the actual reading. Because standard condition, we can calculate it easily, right? From the standard reduction table that we have learned just now. It's easy. We know we can manage. This one is rather easy. But what we know is, what we need to know is like, okay, if we know the correction factor, if we change the concentration of pressure or whatever condition that we have, we know the correction factor that we know. Then by knowing the standard condition, we know the correction factor. Oh, we know what is actually now the reading of the cell potential. That's the proposal as a first step. That's what we want to do. So that the calculation would be simpler, especially for beginner. Yeah. In fact, this is a concept that frequently used for physical science. Yeah. Always you have the ideal situation, you can set a value that very easy for us to calculate. What we want to calculate is the deviation factor, the correction factors, to come in. So, and make us the calculation become very simple, manageable, and for us to easily that we can think of. Okay, now this is called the nurse equation. Yeah, so we use the Nernst equation. Of course, initially we look at this equation, is sometimes very scary, or so long. In fact, this is a simplified version. The original version is even longer. Of course, to memorize this equation is actually, in fact, very torturing without understanding. Just memorize, and then you have to make use of it. But in fact, this one, the derivation, maybe for let's say pre-U, we normally do not derive for the candidates because it's not that easy. But eventually, if it's going to advanced level, we'll show the derivation from the beginning. Let's say starting from the chemical potential of the system, the real system, then the chemical potential for the ideal case, and the deviation factors. From there, this is actually electrochemistry, thermodynamics, to talk about whether it will happen by itself. That's why you have this spontaneous reaction, non-spontaneous reaction, right? For your galvanic cell. And then by looking at this one's standard cell potential is a term set under thermodynamics because it tells you that whether the reaction will take place by itself. If it's positive value, this is a spontaneous reaction. If it's not spontaneous reaction, you have a negative value. So here, to make it simple, if you look at this Nernst equation, this is a standard cell, this is a cell potential in the real system where you do not have ideal case, do not have standard system. That is equivalent to the standard cell potential, which means ideal case, standard potential. And here, the second terms, we call it the second terms here, it's just about the correction factor. To correct back how much our real system deviate from the standard system, or the ideal system here. You can call it or standard system. This is the correction factor, the second term. This one is you don't have any change. You just have a standard condition. So now you see, if our log Q is a reaction quotient. Okay. Put it aside, what is the definition for reaction quotient? If Q equals to 1, log 1. Okay, take your calculator. What is log 1? 0. So, when Q equals to 1, everything will be cancelled, right? Your standard condition would be the same as your real case. When can we have a Q equals to 1? This is the question, right? Normally, when your product, because when we look at the definitions of Q, the reaction quotient, is the concentrations of the product, which and you have a reaction equations, right? You have the reactants become a product. The concentration of the product divided by the concentration of the reactants. If let's say both are the same, the concentration, both product and the reactant, let's say S and Y the same, 1 molar, for example. And also you have the same, the charge, positive +2, the other one -2, or the first one is a -1, the other one is +1, things like that. Then you have Q equals to 1. Then you do not really deviate from the standard condition. Okay, so by doing so, I hope that this Nernst equation is not that painful for you all to memorize it, right? We know that this is the cell potential for the real system. This one is for the standard condition, and this one, no matter how long is these terms, it just shows that this is the correction factor or the deviation. This 0.0592 actually is not simply a number we pluck from the sky. We actually is equivalent to some of the quantities that we already replaced. Of course, I may not want to dwell into it. I'm sure that if you take out a book, any reference book, they will show you the derivation and how to come to 0.0592. And then N is the number of electrons that involved in balancing the overall reaction. The number of electrons, and this log Q, Q is the reaction quotient. Of course, you do not like to use log. In fact, the original version is natural log ln. It also can, because we all know log to natural log scale, all you need is just a correction factor. Yeah, you just times the correction factor. It is not necessary that you must write it in a log scale. You can write it in a natural log scale. But in the case that you do not want to confuse yourself, because sometimes it's a log scale, sometimes the natural log, then after a while, we also forget which scale that we want to use. Then you just memorize, let's say this refers to the log, this log scale of this Nernst equation. But what I mentioned to you that when, let's say, if you see other people that use natural log scale, that could be already incorporated in a correction factor, so it can be used also. So this reaction quotient, again, you look at the definition is the oxidized form divided by the reduced form, and you use the concentration. Of course, at your lab, this course CHM 096, you still use concentration. And a lot of time when you go to thermodynamic, when you calculate the equilibrium constant, this reaction quotient is related to equilibrium constant. We normally use concentration for calculation, but of course, when you go to higher level, this is not precise enough. Then they will say, that, okay, actually we have to use the activity and to replace the concentration. But that doesn't really matter now. Forget about that. Yeah, because the situation that you have right now is very close to ideal case, even though you do not have a standard situation. So we assume we can use the concentration to calculate the reaction quotient. Now again, this reaction quotient, the definition is the product, concentration of the product divided by the reactants. This X and Y is related to the charge of that particular species. Okay. So do you have any questions for this Nernst equation before we actually go for the calculation? I hope that not too tough. So if you couldn't memorize the equations, I think this shouldn't be a problem. Normally you will be given this equation, right? During the exam. Yeah. Okay. So Nernst equation. So should we actually memorize this? I would suggest not necessary, because if you really want to memorize it, I will find it is really too painful. Yeah. Of course, I just look at it mathematically, right? What if you have Q less than 1? Just take out your calculator, right? If your Q is 0.9, you have a bigger value of this correction factor or not, or less, right? Then you know your E cell is higher or lower. When you have Q more than 1, and let's say 1.2, 1.5, what would be your value? Yeah, of this correction factor, and what would be your E cell? So by doing so, basically, you do not need to stress yourself for this description here. Of course, no problem, you can go through and read it and try to memorize it. But in the case that you find it a bit painful for you to do so, no problem. Yeah, just refer to this equation. Yeah, you know that ideal case Q equals to 1, right? Yeah. So if you just play around, Q is less than 1, Q is more than 1. Yeah, then you can predict whether your E cell is higher or lower when you have Q equals to like more than 1 or less than 1, things like that. Yeah, you do not need to always memorize the description. Okay. Okay, now look at this example. Yeah, you have both copper half cell. Now you need to calculate the cell potential when you have different in concentration. Yeah. Okay. So for anode, we know that we need to have the oxidation so that you see the less blue become darker blue. Yeah. Because we need to eventually the cell potential becomes 0, right? But at the beginning, the less concentrated one, right? Less concentrated with copper 2 plus is less. So we want to generate more copper 2 plus. So that's why we put it as this anode oxidation. We want to have a more copper 2 plus. This is darker, right? Darker blue. So what we want is eventually we want it to be a light blue. So which means we want to have less copper 2 plus. So eventually this cell, right, as I mentioned earlier, you have the same color of blue after some time. So then this is cathode. So please take a note here. This is a electropotential, standard electropotential that you copy from the standard reduction table. Because two of them are copper, that's why you have 0.34, right, for both sides. This is under standard condition. Standard condition, okay? So now you look at your Nernst equation here. Look at your Nernst equation, This is the cell potential in actual case where you have different concentration. And this one is the standard cell potential that is standard condition plus a deviation factor. Here, deviation factor. So the standard cell potential, this is standard. Both under standard condition is 0.34. So one is positive value, one is negative value. So, which means the standard cell potential would be 0. Under standard condition, because under standard condition, both actually 1 molar, right? So it's 0. So the deviation actually now comes to the deviation factor here. So now it's important for us to actually put in the value of the constant, to replace, substitute the value for what is the concentrations of the product, what is the concentration of the reactants in the reaction quotient. So the deviation actually right now is here. So this is the correction, that we need to input into the Nernst equation. So the reading of the cell now is 0.07 for this concentration cell. The standard cell potential, the standard condition, the cell potential is 0. But the actual cell potential, when we change the concentration, the reading is not 0 because there is concentration fluctuation in the cell. We got reading, and the reading is 0.07. This 0.07 volt tells you that this is the value that deviates from the standard cell potential. I know it's a bit tough to grab this concept, but that's how we will look in to solve the problem while using the Nernst equation for the concentration cell. We call this a concentration cell. When we call concentration cell, means that we have both the cathode and anode, the same type of electrode, just the concentration that is different. Okay, any questions? Okay, if not, what if now it's not as simple as before, right? Both the electrode are the same, right? Now, what if we don't have the same, Now we have nickel and chromium, and both have different concentration. Just now we have both cathode, anode, copper, right? Now we don't have, one is nickel, one is chromium. Okay, so, and then we calculate the cell potential. Okay, first, problem that we have to solve is, the strategy that we need to follow is, decide which one is cathode first. Which one will undergo oxidation? Which one is undergo reduction? Because we were not told in that time, right? In this problem, we were not told. But we were told that this is a galvanic cell, which means at the end, the standard cell, or the cell potential must be bigger than 0. Because it's a galvanic cell, it must have a positive value for the E cell. So we look at this, this is a more negative potential, means that it would tend to be from right to the left. So by doing so from the right to the left, you see, this is the overall reaction. This would be oxidation, and not this would be the reduction cathode. So in that case, by knowing so, we already straight away know that the standard cell potential, because we know which one is cathode, which one is anode in the standard way. Yeah. But now the next step is we need to calculate the correction factor, because we do not have the standard, the concentration in the standard way, which is 1 molar. Yeah. So it is not 1 molar. That's why we need to use the Nernst equation. We solve the problem. Let's say this is a Nernst equation. We already get this value, the standard cell potential, right? Because we have the standard condition. Now we just need to calculate the correction factor, because we do not have the concentration at 1 molar. Yeah. And we know which one is the in oxidation form, which one is a reduction form, and we know what is the concentration of each species as the concentration as well as the charge. Do you see the charge here? 2 plus, 3 plus. Yeah, we see that. Then by putting in all the necessary information in the reaction quotient, yeah, we calculate this Q value and 6. 6, where do you get 6? That involves 6 electron here when we balance, because 1 is 2, 1 is 3, right? Times 3 times 2, then overall we have 6 electron that involve, and we have 6 here. So we have this value that calculated, yeah, from the standard reduction table, yeah. So we have this one calculated, yeah, here, yeah, here, yeah, this one, yeah, the E standard cell potential here, put in here, yeah, this one, 6, the N equals to 6, yeah, from the overall reaction here, because this one 2 and 3, we have to balance the equation, 2 times 3, 3 times 2, we have 6, yeah. And then the concentrations of the chromium 2 plus and the nickel 2 plus. Yeah. And this one, 2 plus. Yeah. Here. So, sorry. Chromium, chromium here, chromium 2 plus. Do you see when we balance the equation? This is 2. This is 2, because we need to balance the overall reaction. This is 2. Do you see this is 3 here? This is 3. So when you have 2 and 3, remember in your reaction quotient here, you have to power the exponent accordingly. And then when you make the calculation of this correction factor, corrected to this standard cell potential that you calculate here under standard condition, this is your standard, this is your cell potential that you will read from this cell that not under standard condition. So of course, this is a rather tough calculation. So you need more practice. Yeah. Definitely, you need more practice. So now we have 5 minutes. Yeah, please try for these questions. This problem, the checkpoint 7. Yeah. We have 5 minutes. Yeah. Okay, welcome back. So I guess after the 5 minutes try, okay, do you have any problem? Okay, let's see the solutions. So first of all, when we have this problem, so we need to decide which one would be the cathode, which one would be the anode, which means which one will have the oxidation, which one will have the reductions. As we know that the one with the higher concentration, we'll put it as in a reduction form, and the one that with less concentration, then we put it in an oxidation form. So because we have the same cathode and anode, that's why the standard cell potential, standard cell potential in standard condition, which means the concentration at 1 molar would be 0, because we have both the cathode and anode have the same electron. Now, when we look at the Nernst equation, so we know that the standard cell potential would be 0. All we need to do is just to take care of the correction factors here, the second terms. So now we look at this, so this is we just look at the concentration. We know that, this is the oxidizing form, like 0.1, and 10 is the concentration in the reduction form. So whether we have the exponent or not, please, you may not be able just to guess by reading the question like this. I would suggest you write down the overall reaction by yourself to know that whether you should have power 1, power 2, or power 3. You need to know that whether what is your n. In this case, it's simpler. It's n equals to 1 and power 1, power 1. But that's, you should not assume you will know that by just reading the question like this. You need to write the overall reaction in order for you to get the answer like 0.12. So if you know some idea on how to make use of the Nernst equation, then this Nernst equation is not that worrying when we look at it, because it's quite long, right? So it seems to be, it's manageable, because right now we know the basic concept. This one is just a standard condition, and the second terms here is just the correction factor that we need to deal with when we do not have the standard condition. So with that, this Nernst equation becomes something like a user-friendly equation to us. Okay, so when you have the questions number 2, I hope that you can try at home. Even though the questions now become longer, when you look at it, it's like, oh my God, how to start with? Do not worry, using the same principles. First, start to write your half reaction, overall reaction, balance it. Then, because you do not have the standard condition, then make use of the Nernst equation. If you just follow the step, then most likely you can solve the problem without much difficulty. Now, with that, I think we achieved the goals for today. So we take care of the 2 topics that's rather tough. How we initially talk about the standard electropotential, the standard cell potential. Then it's a non-standard cell potential that we make use of the Nernst equation. So this is my contact details. And if you have any issue on these topics or things related to thermodynamics, you can actually drop me a message. So I hope that I guess I stress you quite a lot, 2.5 hours with lectures and then exercise and all these. But I hope to show you that even though when we talk about galvanic cell, when we talk about standard cell potential, all this seems to be not related to our life, because I'm talking to my, based on my personal experience. In the past, when I studied this subject, I will always think that this is nothing to do with my life, So I feel very, very torturing when I want to study or memorize the equation that I feel that I will not use for the whole of my life. Things like that. After my graduation, I will forget about the equation immediately. All I did was just to fulfill the requirement for exam. So it makes my study become very, very challenging. But in the case that we know, this is only the basic. Only when we understand how the electron flow, for galvanic cell, later maybe for electrolytic cell, to generate, to split the water, and later on to make use of the splitting of the water, and then to store it into the battery, and we use it for the renewable energy. Then we know that all these basic ideas, basic knowledge that we learn is for us to make a better products. A better products that we use from things like handphones, smartphone, tablets, that now we can no longer live without it. Imagine one day you go out without your handphone. You feel so handicapped, right? You can't survive. You feel like, no, I must go back and just grab my handphone because we just can't live without it. And now that is why we need more and more scientists. We need more and more talented students to come and join the force, how to make better and better product in a more sustainable way. But everything starts from a small steps. Learn the basic. Grab the idea. These things seems to be not related to your life just because we do not realize it. But if you think about people, that's about the battery that we use. That's about the renewable energy that we need to use. So I hope with that will motivate to spend a little bit of time for this topic, electrochemistry. Thank you. So I welcome questions from you all.
Thank you so much, Professor TSCHM, Dr. Chan Chin Han, for a very good and clear explanation about the topic. So next, we're going to have a Q&A session. So if students have any inquiry, please, you may turn on your mic, and those from the YouTube, you may write your question in the comment section. Okay. Does anyone have any question?
May I give a question?
Okay, Muhammad Zaki Nawari, please.
Okay, I want to ask about some diagram that we have seen in the slide of the zinc strip and the copper 2 sulfate solution. So that, like Professor Dr. Chan said just now, she said that the reaction is complete cell. So how do we define the electrode of the of those complete cell? Because
okay, because we always have this understanding when we have the complete cell, it has to be 2 electrode. 2 electrode is the things that actually fix into our mind. That's why we expect we should have 2 half cell. Then only is complete. That's why when we see this is one beaker, right? Let's say, in the electrode inside, we thought it is a half cell. It is not a complete cell. That's our mindset. But now, think of it. You have a metal, for example, ferrum, Percy, you put in the water. Just put in the water. After a while, corrosion happens. Where is your complete cell electrode, cathode, and anode? Reaction take place, right? And this is spontaneous reaction of corrosion. So that means, of course, ideally, for us to understand easily, we should expect to see it with our naked eyes, cathode and anode, 2 electrode. But in the case of this zinc in the copper electrolyte, right? So we may not have the electrode percent as we see with 2, but the oxidation and reduction do take place in that cell. So the electrode, physically, what we see the electrode is something like just a reference. If we have, okay, fine. If we don't have, also can. But the main discussion for this section is actually oxidation and reduction. It's not so much about cathode anode. It's about oxidation and reduction, where our zinc being oxidized and the copper 2+ being reduced. we have oxidation and reduction take place in a cell, even though the copper, you don't see there is a copper electrode, but the reduction did take place. That's why you see the depositions of copper onto the zinc electrolyte. Reaction completes because we have exchange of electron in that sense. So of course that is a very weird example certainly appears, right, in this course, because all the while we show you we have a left and a right and these two anode and cathode, right? So suddenly we see one beaker. That's really, and when I look at the diagram, I was like, oh my God. Yesterday actually, in fact, how am I going to make the student realize that it is a complete cell, it is not a half cell. But if you relate it to your daily experience of corrosion, you don't see you need two pieces of metals. Am I correct? You don't need to have two different pieces of metals and corrosion will take place. The ferrum will just corrode and is it, right? I hope that I answer your questions.
Yes, thank you, Prof.
Okay, thank you, Muhammad Zaki. Does anyone has any more questions to us? No more questions? All right, thank you. So thank you to all students for your attention, and I guess that Professor Dr. Chan Sin Han has given a very clear explanation on this topic. So this marks the end of our session. I would like to thank our distinguished speaker, Professor TS CHM Dr. Chan Sin Han, all lecturers, and students for participating in this professorial lecture. And I would like to extend my apologies for any flaws during the program. We hope that this session will be fruitful and beneficial to all of us. Till we meet again in the future, stay safe and take care. Thank you.
Thank you very much. Yeah, thank you. I hope to